try to hit the forward button. There it goes. And I digged out the first slide. Yes. Okay. So I grabbed a few. Let's go through the process again of graphing. Let's go through this, make sure we get this down. The graphing is one of those topics that is very procedural. So it is mastered simply by practice. That's all you have to do is practice it. No big concepts involved, just some basic memorization for periods of the basic functions and things like that. But overall, it's just it's a process, so we just have to practice it. And if you go into the study plan in my math lab, you can go to the graphing section and you can practice as many of them as you want. Or if you're creative, which hopefully you are, you can just start writing down numbers. Pick a function, secant, and just write stuff down. Put a 3 there. Put a pi x plus, who knows, whatever you want to put over here. Pi over 2 minus 3. Practice that. Then all you have to do is go to Desmos, type it in, and you know whether you graphed it correctly or not. So you've got to initiate practice on your own at this stage of the game. You've got to start figuring out a way to know whether you're really 100% comfortable with the topic or not. And if you're not, go into my math lab to the study plan and practice, or create your own problems and practice. And remember that when you're practicing, there's a couple of things about practicing. In my math lab, if you're doing the homework types of practice, you want to practice in a way where you're not always looking at the help buttons. You know, that's an important thing to get to wean yourself off of if you've been dependent on them. The other thing is that when you're studying, it's very easy to sort of get a false sense of security with your expertise if you stick in one section at a time. Like if you do 20 questions from section 1, one after another, after another, after another, after another, by the end of it, you're probably not reading the problem. You probably just sort of know the process so well, which is fine. That's a good way to study at first. But before an exam, you want to try to study the way we create exams. We as teachers go, we grab 2 questions from section 1, 2 questions from section 2, 2 questions from section 3, or something like that. So your last stage in studying should be like that. Do 1 question in 6.1. Do 1 question in 6.2. Do 1 question in 6.3. 1 in 6.4. 1 in 6.5. Then go back and start over. So that you're getting into the habit of looking at the problems out of context, and you're getting into the habit of looking at the instructions. If you only do questions from 6.1, you sort of forget to read the instructions and identify what the process is with that instruction, because you're getting good at just writing down the answers. It's just essential that you know what you're being asked to do. So you want to make sure that you are really careful about reading the instructions and identifying the process for those instructions. You know, like a lot of times you'll get to a test and like, oh, I have no idea what you're asking. Well, that means that you got into the habit of doing the process and not identifying the process with the instruction. Because the instructions of the book are the same as the instructions they're going to give you on the test. There's no surprises. So you just want to make sure you're in the habit. Sometimes with online homework, it's very easy to look at help me solve this and not really think carefully about what they're asking. You want to get into that habit of thinking carefully about what they're asking and what the process is that matches that question. So do some good thorough studying as the last piece of your prep for the test. So with this graphing problem, we factor first. Whenever we have an angle that has a leading coefficient other than 1, we need to factor that out first. So that pi has to factor to the front. Now this is a reciprocal function, so we also have to convert it. We have to create a guide function. So let's just do it all at once. We're going to switch cosecant to its reciprocal. That's sine. And then the pi factors out pretty easily there so that we have pi times x minus 1. So there's our guide. And then we write down the 5 characteristics for the guide. So these are for the guide. And we just look left to right. So we see a minus in front, so yes, there is a reflection. And how about amplitude? So it's going to be the absolute value of the leading coefficient. So it's positive 2. Amplitude's always a distance, so it's got to be positive. We would never want a negative amplitude. And this is for the guide. So for sine, when we look at the function we're actually trying to graph, cosecant, the word amplitude makes no sense because we know that cosecant has those arches that go up forever and those arches that go down forever. So it doesn't make sense to talk about amplitude because the meaning of amplitude is maximum distance, and there is no maximum distance if the graph goes up and down forever. So that amplitude is for the guide function. Period. What is the period of a basic sine function? 2 pi. So basic sine, basic cosine, 2 pi. Tangent, cotangent, basic pi is the period. So now we have to adjust this period. So the number that is the leading coefficient of the angle, that is our period adjuster. And we have to divide the basic period by that coefficient. And so this one is interesting because we end up with a period of 2. We end up with an integer period. All of the examples I've done thus far have had a pi in the period. We've had a period of pi or pi over 4 or 3 pi or whatever. Right? So this is our first example that I've done where we have a period that's an integer. We should actually find this very easy to graph because we don't have to be splitting pies. Right? If we have a left and a left and a right endpoint with pies in them, you have to add them and divide by 2. It's going to be a lot easier with integers. Or should be. The phase shift is what? Positive 1. We look inside the factored angle. We see a negative 1, so the phase shift is positive 1. That means to the right 1 unit. And then the vertical shift is also 1 from the outside. Go to our graph. And step 1 for our graph is always the phase shift. So we're going to put the phase shift on there. And let's see. Yeah, this one's not too crazy. Put phase shift on there, step 1. And then what's step 2? So our whole goal is to create an interval on the x-axis for which the first period lives in. The first period is going to be starting at 1. That's the left endpoint. And how do we get to the right endpoint to the first period? The period. The period's 2. So that says if we start at 1, we need to go 2 to the right to complete the first period. So we add that, and that will put us over at 3. So if there was no vertical shift, our center line would be right there from 1 to 3. But we now look at the vertical shift. The vertical shift is 1. So we're going to lift that center line up a unit. So that will be our center line for the graph. Take into consideration the vertical shift. All right. Amplitude comes next. Now that we know where our center line is, we need to figure out how far above and below the center line this guide function will go. 2 is the amplitude. So we need to have enough space on our graph to go up 2 and down 2. And then we have to deal with their shape. And the shape for a sine looks like that. And our key points, 1, 2, 3, 4, 5 key points. And the key points, in conjunction with the reflection, is our next step. Certainly, the key points that are right on the center line, no problem. Those will be right on the center line. But because there is a reflection, the other 2 key points, instead of being up on the left and down on the right, will switch. so that they are down on the left and up on the right. So we're going to put a point there and then there. So that will be our guide function. Any questions up to that moment? So to do a secant or a cosecant, you have to be able to do sine and cosine. No way to do those reciprocal functions without being a master of sine and cosine. Okay. Cosecant is the reciprocal of sine. Anywhere that sine crosses the center line, we will have a vertical asymptote for cosecant. So we have these three vertical asymptotes. Right where the guide crosses the center line. Now we just have to draw the arches. And for a cosecant, the arches are nice and connected. We don't have any weird partial arches. So our graph is going to go down there, constrained by the vertical asymptotes, and up there, constrained by the vertical asymptotes. So that'll be our first period. First period of a transformed cosecant. Can you do that on Tuesday? So let's identify the domain and range. The domain of this function. Whoops. Domain. Let's move that over a little so we can look closer to the graph. So the domain, we have to take away the asymptotes. So it wants to be all real numbers, but it can't because there's some pesky asymptotes. So we have to take those away. And the typical process is to look at the first non-negative asymptote. And where is the first non-negative asymptote? 0. First non-negative. If you wrote 1, I'm totally fine with that. Absolutely. These asymptotes are all 1 unit apart, right? So the one to the left of the one at 1 is actually right there. So that one would be the first non-negative one. I'll move my y-axis over just a smidge, I think. So that would be the first non-negative one. That would be right there. But it doesn't matter. It's all the same. My math lab's going to want to is going to want you to find the first non-negative one. It doesn't matter though. On the test, if you wrote x not equal to 1 plus k, totally fine. But you could, the cleanest way would be to say x is not equal to k. Start at 0 plus 1k. Coefficient of k is the distance between consecutive asymptotes. That's just 1 in this case. So either of those, totally fine. Range, we start way down at minus infinity, climbing up the y-axis, looking for y values. And there's y values all the way up as you climb the y-axis until you get to -1, and then they abruptly stop. They keep climbing up the y-axis, and they start up again at 3. So that would be our range. And make sure that on the range that it's very clear that you're using brackets because you include the -1 and the 3, so a bracket, not a parenthesis on those. Do another one. So another reciprocal function. So the only two that we have to do this whole guide thing for are secant and cosecant. Those are the only two reciprocal functions that we use this process for. Cotangent is the reciprocal of tangent, but we don't use this process for cotangent. only for secant and cosecant. So our guide, the reciprocal of secant is cosine. And now we have to factor. And any questions on that factorization there? -2 is in front of the angle, so we're going to factor it out of the two terms. And we have to make sure that the distribution gives us back what we started with. -2 times x is -2x. -2 times positive pi over 2 is negative pi. Okay with that? All right, now, last class we talked about the leading minus on the inside of a function, and we looked at the odd and even properties for trig functions. And what we saw last time was that if you had an even function, you could just erase the minus sign for an even function. And for an odd function, that minus on the inside jumped out to the front. So that's what we looked at last time. Let me just draw a quick little reminder up here of why cosine and secant are the only two that are even. Let's just remind ourselves why this is true. Really important to be able to visualize this. Need that to be a little lower. If we consider that angle theta, then this would be angle minus theta. The terminal point always has coordinates cosine of the angle that dropped you at that terminal point, comma sine of the angle that dropped you at that terminal point. So that's our theta. And if we go down this way, that's a minus theta. So that terminal point has coordinates cosine minus theta, sine minus theta. So the coordinates of the terminal point are always cosine comma sine of whatever the angle is that got you there. Could be negative, could be positive, could be multiple revolutions, doesn't matter. And this is a unit circle. And hopefully it's totally obvious that they share an x value. That and that are equal because they have the same exact x value. Right? Everyone agree? You can see it visually, right? The x value is right here, and that's the same for both. So that means the x coordinate of that point and the x coordinate of that point are equal. So cosine minus theta is equal to cosine theta. But sine of minus theta, the y values there have the same magnitude but opposite direction, so sine of minus theta is minus sine theta. This top one is an example of an even function. The bottom one is an example of an odd function. So even, cosine and secant, all the rest are odd. Even, you erase the minus. Odd, the minus jumps to the front. Our function that we're dealing with is cosine. So that minus right there just vanishes, just disappears, because it's an even function. All right, so now we have our guide, our simplified guide. We read left to right. No reflection, amplitude is 3, period is 2 pi over 2, which is pi. Phase shift, opposite of what we see. Vertical shift, exactly what we see. 5 characteristics. And we're going to start at our phase shift. I'll just put a y-axis right there for the time being. Probably have to move it a little bit. We'll see. All right, phase shift, minus pi over 2. So we always start with the phase shift. And then, step 2. What are we going to do to the phase shift now? Add the period. Exactly. So the phase shift, left endpoint first period, add the period, and we get to the right endpoint to the first period. So what do we get when we add pi to negative pi over 2? Positive pi over 2? is actually not too bad. Stick in our vertical shift of -1, so that's right there. That forces our center line to be across there. Amplitude is 3, so we need to have enough space on our graph to go up 3 and down 3. So 1, 2, 3. Stretch that y-axis. So down 3, that makes that -4. Go up 3, and that would be at 2. So I've counted properly. Now we've got to take a look at our shape, the shape of our guide. We're dealing with a cosine, so we've got the bird. That is our shape that we have to squeeze into the rectangle that's kind of implied here. We have a rectangle that's implied, bottom at -4, top at 2, left side at -π/2, right side at π/2. So we've got that rectangle we have to squeeze that shape into. Let's put our 2 intermediate points here, because that is where we cross the center line. So for sure, those points never change, whether there's a reflection or not. The center line points are the center line points. And our bird does not get flipped upside down because we have no reflection. So that means middle will be right down there, and then the ends, the top edges of our wings will be right up there. So get that. There's our guide. The guide. The final step is to convert back to our reciprocal function. Anywhere that the guide crosses the center line, there will be an asymptote for the reciprocal function. So those 2 places we have asymptotes. And then we draw the arches. We have a complete arch down in the middle here, opening down, one nice complete arch. But up top we have 2 half arches. 2 half arches up top. Half only. You will lose a point if you draw that. We only want the first period, so that's the first period. Domain and range. What's the first non-negative asymptote? π/4. So between 0 and π/2, that's just halfway in between, so that's at π/4. So that's the first non-negative asymptote. So we can't be π/4, and then how far apart are these asymptotes? Consecutive asymptotes are here pi. Does anyone disagree with that, other than me? π/2, right? The period is pi, so from there to there is pi, so the asymptotes are half a period apart. Half a period apart. So that's our coefficient of k. That will be our coefficient of k. So k, again, you don't have to write this, but k is understood to be an integer. So it could be a negative integer, positive integer, so it's one of any integer. That'll get all of our asymptotes. If we look at our picture, this asymptote right here is corresponding to k equals 0. This asymptote would correspond to k equals -1, etc. So positive k's will get us the asymptotes to the right, negative k's will get us the asymptotes to the left. The range starts way down, -∞, coming up the y-axis until we get to -4, include, and then no range values until we get all the way up to 2. That will be our range. Feel better than it did last week? graphing last Thursday. So let's get to our crazy tangent and cotangent. All right, let's see. You guys factor this one. See if you can factor a -4 out of there correctly and efficiently. Without the use of the calculator. Then go ahead and write down your 5 characteristics. Hopefully you were able to factor that properly. There's the factorization. What do we do with that leading minus? So tangent is an odd function. The only two that are even are cosine and secant. The rest are odd, so minuses jump to the front. These minuses have the power to jump from the inside of the function to the outside of the function. There you go. And now you're going to write your 5 characteristics down once you've got that far. Yeah, Richard.
Sure.
Sure.
On my paper, it doesn't have the minus sign in front of that 4. Didn't show up in there.
Well, that's interesting.
We didn't have a space for it.
Yeah. Yeah, I might not have updated that. I might have wanted to toss this in at the last second and forgot to update that.
And why does the, so explain to me again why the minus sign in front of the pi, why it should probably be.
Somebody, why is the minus turned to positive in front? So we factor out the -4 there so that when we distribute back, we're going to get to this minus 4x and negative pi, right? -4 times pi over 4, the 4's cancel, we get negative pi. And then that minus sign jumps all the way to the front because we're dealing with an odd function. So even function, the minus disappears, but if the function is odd, so if it's sine or cosecant or tangent or cotangent, that minus jumps all the way to the front. So what about if there was a minus in front already? What would happen? Yeah, the outside would turn into a positive coefficient, right? Okay. And hopefully you were able to pull these things off pretty easily. Left to right. Reflection, yeah, we see a reflection right out in front with that minus. Amplitude, that's not applicable for a tangent. It goes up and down forever. Period, the basic period for tangent is pi. And then we have to divide by the leading coefficient of the angle. So our period will be pi over 4. So is this a horizontal compression or a horizontal stretch? Compression, because the period of the basic tangent is pi, and the period of this transformation is pi over 4. So we've compressed the period from pi to pi over 4. So that's a compression. And that fits because the coefficient inside is greater than 1. So greater than 1 on the inside is a compression. Greater than 1 on the outside is a vertical stretch. Horizontal compression, vertical stretch are actually the same. So that all fits with our intuition. And then our phase shift, opposite of what we see. So that's minus pi over 4. Vertical shift, Exactly what we see on the outside. All right, so we are certainly going to start with the phase shift. Like we always do, start with the phase shift. Figure out how far left or right we're going. So I'm going to just put negative pi over 4 somewhere on the graph. Negative pi over 4. Second step is definitely the period. Now, for every function other than tangent, we add the period to the phase shift. The other 5 functions, we add the period to the phase shift to get to the right endpoint. But for tangent, the phase shift corresponds to the midpoint of the first period. So that minus pi over 4 is not the left endpoint of the first period, like it is for the other 5 trig functions. For tangent, it's right in the middle. If we were to look at the first period of a basic tangent, that first period looks like that. All the other first periods start right at the y-axis. But for tangent, the first period starts at negative pi over 2 and ends at pi. So the basic characteristic is different here, where the phase shift is going to correspond to the middle of the graph, not the left edge of the graph. So we have to take an interval of length pi over 4 and place it right there where the midpoint is negative pi over 4. So how far to the left and right do we have to go to get a total width of pi over 4? Pi over 8 each direction, exactly. Because half of pi over 4 is pi over 8. We want half of it to the right and half of it to the left. So we're going to have a mark here at negative pi over 8. And then this one, pi over 8 to the left of that, would be minus 3 pi over 8. Minus 1 pi over 8, minus 2 pi over 8, minus 3 pi over 8. And that's where our asymptotes will go. Yeah, good. And then the rest is pretty similar to the other functions. We go to the vertical shift. It's 2. So we need to go up 2 on the y-axis. That's where our center line will live. Right up there. That was that. Let's try to draw that a little bit better. Right there. And for a tangent, the shape of tangent is up to the right. And there's just one key point right there. That's tangent. Cotangent is down to the right. Tangent is up to the right. So our one key point right there. And now, if we wanted to be more accurate rather than less accurate, we would say to ourselves, hey, there is a leading coefficient that's greater than 1, so it should look steeper than a basic tangent. There should be a vertical stretch there. So if we want to try to incorporate that concept, we would have a steeper tangent, and we'd draw it like that. But you don't have to plot specifically another point. You don't have to try to pick an x value that's between... Oh, whoops, reflection, thank you. I can read your mind. So we always have to look at our shape and, and our reflection. Thank you. So instead of up to the right, we're going to go down to the right, but we're going to do it steeply. So like that. Yeah, reflection and shape together. All right, the domain for this guy wants to be all reals, but it can't. You must deal with these pesky asymptotes. All right, first question. How far apart are these pesky asymptotes? Pi over 4. So for a tangent or a cotangent, the period is also the distance between consecutive asymptotes. Because tangent and cotangent, we have those goalposts around. Right at the edges. So that will be pi over 4. Okay. let's try to be thoughtful here. What would the first non-negative asymptote be? So here are pi over 8. So if these are pi over 4 apart, we would have to go from, if we wanted to get the first one that's not negative, we would have to add pi over 4 to that. Pi over 4 plus negative pi over 8 is going to be positive pi over 8. Oops. Positive pi over 8. So that would be the first non-negative one. It would be right there at pi over 8. All right, let me move it over just a smidge. So it looks a little bit more accurate. All right, so we would say not equal to pi over 8 plus the distance between consecutive asymptotes multiplied by our counting integer k. So we're going to write on the graph what asymptote belongs to what value of k. K equals 0 would be there. K equals minus 1 would be there. K equals minus 2 would be there. And the range, of course, all reals. Okay, so that's the one oddball. Period has the phase shift as a midpoint. All right, let's go to cotan. All right, you guys factor that and pull off your 5 characteristics, and then we'll graph it. Any trouble factoring that? You know, if you're baffled by factoring the pi out. This is a good sign. On Tuesday when you were doing this, there was a lot less scribbling and a little more flipping through pages. So it must be sinking in. You must be grateful that you have a test coming up. Factored form up there. Let me know if you had trouble with that, if you need any help. All right. Reflection, yes or no? Yes. Yes. Amplitude? Not applicable. Cotan goes up and down forever, so it has no amplitude. Don't want to lose a single point for doing something like that. So no amplitude there. Period. 1. So the period of basic cotan is pi, but then we have to divide by the leading coefficient of the angle. So we have to divide pi by pi to get 1. Phase shift will be 1/2, positive 1/2, opposite of what we see, and the vertical shift, -1, exactly what we see. All right. So cotan follows, just like the other trig functions that aren't tangent, we start at the phase shift and add the period. So let's see, our phase shift is positive 1/2. So we'll put a tick mark right there, positive 1/2. And then where do we end up for the right end point of that period? 1.5, 3/2, 1.5. Let's see, let's see if I can stretch that a little bit, try to make it look, that's 1/2, and that's 1, and then that's 3/2 right there. And cotangent, asymptotes on the edges vertical shift is down a unit, minus 1. So that tells us that the center line for this graph is down here. Now we're going to go to shape. And for a cotangent, the shape is down to the right. Ooh, that's a terrible cotangent. Down to the right with one key point. So our key point is going to be right in the center of our center line. And then here we just have to be careful. Cotangent is down to the right, but we also have a reflection, so it's actually going to go up to the right like a tangent. And if we wanted to be more precise instead of less precise, if we look out in front, the leading coefficient there, ignoring the minus, is a 1. So that should have the same steepness as the basic function, so maybe like that. And the domain of this function wants to be all reals, but it can't be. Take away the asymptotes. First non-negative asymptote, 1/2. So x can't be equal to 1/2 because there's an asymptote there. The function's not defined. And then we figure out how far apart consecutive asymptotes are. They're 1 unit apart, so it's just going to be plus 1k. And then the range will be all reals. Come together. I see the joy. I can see it in your eyes. Well, at least I'm hoping it's joy. At least it's competence. You're looking competent. Okay, so once again, you can always check in Desmos. Type in your function. Make the x-axis have pi over 4 or pi over 2 or whatever the step is that you want. Really easy way. If you want to practice tangent functions, just throw in some numbers, practice your factoring, and check your graph. So really easily. Here I graphed a sine, a cosine and a secant, and it's always going to be the guide function's just going to sit right there as a nice little guide template to graph your reciprocal functions. So use Desmos for some practice. Any questions on graphing before we go back and start reviewing from 6.1? Feel pretty good with the graphing? Seems like it, but I've been here before, where everyone looks like they think they know how to graph. The biggest mistakes in graphing are messing up the tangent thing. So in tangent, make sure the period goes over the phase shift, you're not adding the period to the phase shift. That's one common mistake. And then the other common mistake is being a factoring, not being a factoring ninja, being a factoring bozo, and not factoring correctly. So double check your factoring, because you can all factor by now. So it's just a matter of double checking, because it's very easy to just make a mistake and then not catch it. So double check it, because that's a very common place. And the most common one that I see is this kind of thing. If you have 2x plus pi, if you're going to factor out that 2, it's going to be x plus pi over 2. If you're factoring a constant out of pi when it's not in front of it, you have to introduce a factor of it in the denominator. So that's the most common factoring mistake that I see on this test. And again, if it's not clear to you how you just jump to that, obviously you can double check that you did the right thing, but if you need to, you can always multiply this by 1. 2 over 2 is 1, and then you have a common 2 that you can factor out, and you're left with pi over 2 there. So whatever it takes, just be aware of that one nuance, because that is a common place for mistakes to happen. All right, back to right triangle trig. So back in the day when we were solving these, we found the 3 unknowns. So we were given 3 pieces of information. We had to find the other 3. So in this particular triangle, usually we would go for the inside angle first over there, alpha. So alpha is going to be 90 degrees minus 39 degrees, 32 minutes. So we just have to do that subtraction. Usually, I find it easiest if you stack these and you borrow from the degrees to create some minutes. So 60 minutes is 1 degree, so we can take 1 degree away from 90, leaving 89, and turn that degree into a bunch of minutes. We need some change, so we can subtract the 32. So then we subtract, we get 28 minutes, and we get exactly 50 degrees. So that will be angle alpha. Good? All right, now let's go for the two sides that are unknown, the A and the C. It doesn't matter which one we go for first, and it doesn't really matter whether we use the angle that's given to us in the triangle or that, because we didn't do any rounding there, so that angle is totally fine to use for future computation. I'll just use the 3932 because it's kind of in the picture here. So if I want to, let's solve for A. What trig function would I use if I wanted to get that, that, and that? Tangent, because we're not using the hypotenuse, right? Anytime we're doing a trig ratio without the hypotenuse, it's going to be tangent. Yeah, good. Caught yourself. So tangent of 3932 will equal opposite over adjacent, so that's 28.4 divided by A. Then we'll do a multiplication by A and a division by tangent of 3932. So A will equal 28.4 divided by tangent 3932. Now we just have to type it into our calculator correctly. If you are not sure how to do your units, come see me during the break and we'll figure it out if I don't know off the top of my head if you have one of those different calculators. Tangent 39. This is actually faster on the little calculators. You can get to the angle menu a little more quickly. And I am coming up with 34.4. Somebody else get that? Yep. Okay, good.
I got 34.6.
34 point. So my guess is that did you enter degrees in minutes on that angle?
No.
Oh, well, that's a problem. So if you're doing tangent, you're doing 39 degrees, you have to go to your degree menu, grab degrees, and then 32 minutes, we type 32, go back to there and come over to minutes. Like that. And why did I round to 1 decimal point? Because the other one's rounded to 1 decimal point. We're not dealing with significant digits in this class, but if this is rounded to the nearest tenth, then let's round that to the nearest tenth, and let's round C to the nearest tenth. So we'll just be consistent. On the inside, it's rounded to the nearest minute, so we'll round that to the nearest minute. So we'll just have that same sort of consistency. Now, if we want to use that same side over there, and the C, and the angle, what trig function will we use to get it? So cosine, what'd you say? Sine. Okay, good. Sine of 3932 will equal opposite over hypotenuse, so that looks like 28.4 divided by C. We'll have to do a similar type of computation that we did over here. We're going to multiply and divide. So we'll get C equals 28.4 over sine 39 degrees, 32 minutes. Type that into your calculator and rounding to 1 decimal place. What do you get? 44.6. Confirmation by? Yep. Good. 46, 44.6, good. All right. There will be no more than one of those on the test. No more than one. I know you'd like to have each question like that. No more than one. So there will be one of these things. This was the application in the textbook was the Golden Gate Bridge problem. So our goal is to figure out the height of this triangle. We have these two angles, and we know that, hopefully you can see that 80 is just from there to there. All right, so here we have to set up a system of equations and then do a simultaneous solve type of thing. We have an unknown down here that we will definitely be using. That's x. Call it whatever you want. I'll call it x. So the inner triangle, we have tangent of 55 degrees is equal to h over x. The outer triangle, we have tangent of 40 degrees is equal to h over h plus x. What? H over what? 80 plus x. Thank you. There we go. So those form a system. We have two equations. We have two unknowns. The only one we care about is h, but if you are more comfortable solving for x first, totally fine. Doesn't matter. Top equation, if I multiply both sides by x, we end up with x tangent 55 degrees equals h. Now, if I'm trying to find h, this would make a natural substitution for h, which would leave an x. So that would mean we'd solve for x first and then back sub to get h. If I just want to solve for h, though, I'm just going to do this. I'm going to say, hey, I want to substitute out the x. So if I want to substitute out the x in the other equation, then I'm going to plug that in for x. So I'm going to do that. So I'll take that second equation, tangent of 40 degrees, and we're going to sub out the x. Down below, it's 80 plus, and we have this. And there's lots of ways to proceed from here. One common thing that you may do before you even plug in that x is multiply 80 plus x to the other side so that you've eliminated one of the fractions right away. Totally fine. What I'm going to do right now is multiply everything on the right by tangent of 55. And that will be another way to clear out that tangent of 55 that's in a denominator. So I'm going to multiply that by tan 55. I'm going to multiply this by tan 55. And I'm going to multiply this by tan 55. So what I've done is multiplied by 1. I've multiplied numerator and denominator of that fraction by tangent of 55 over tangent of 55. I shouldn't say I've multiplied numerator and denominator by. I've multiplied the top by tan 55 and the bottom by tan 55. And then it had to be distributed. So we multiplied by tan 55 over tan 55, which is 1. OK. So that would give us, we're going to just do it one patient step at a time. Over here we'll have h tan 55 in the numerator. And then in the denominator, that tan 55 cancels with that tan 55, leaving just h over here. And then on this side, we'd have 80 times tan 55. That. Now we're going to move this entire, now we need to clear this big denominator, so we're going to move that whole thing to the right, to the left. We're going to multiply by that entire denominator, both sides. So when I multiply both sides by that, I will get this. I'm going to do one distribution step in my head here. we multiply both sides of the equation by 80 tan 55 plus h. On the right, it cancels with the denominator, giving just the numerator. But on the left, we have tan 40 multiplied by this two-termed expression. So that tan 40 has to jump across to both of those. So that's what I've done, is distributed the tan 40 to both terms. All right. Now, this equation is linear. And with linear equations, you collect the variable on one side and you put the constants on the other. You put the terms that have no variable on the other side. So the two terms that have h's are right here. So I've got to get those on the same side so that I can consolidate and have a single h. So let's do it this way. So I'm going to leave this 80 tan 40 tan 55 alone. And we'll, what's that little dot there? And we'll move the tan 40, h tan 40 to the other side. And then what are we going to do over there on the right-hand side? Factor out the h. H is showing up in two different locations. If we're trying to solve for h, somehow we have to have only one h over there. And to get one h from 2, we factor. So once we factor that out, now we have one h, and we can isolate that one h very easily. That h can be isolated with a simple division. That doesn't look like it wants to work. Wanted to cheat. All right. Just ignore all those weird black lines. All right, so last step to isolate h. Divide it out. Divide out that coefficient, if you will. Divide out this whole factor over here, and that will isolate h. And I'll put h on the left. So h will be 80 tan 40 tan 55, all divided by tan 55 minus tan 40. And now the hard part. Type that into your calculator. We'll round to the nearest foot because that was to the nearest foot. So see if you can do it. So numerator, be generous. Wrap everything up. Make sure you're in degree mode. Make sure you wrap your entire denominator. Nicely wrapped denominator. And to the nearest foot, I'm getting 163. All right, so there we have it. 163. Time for a break. Take 10. Ready? Break. Take 10. Resume. Let's do a couple navigation problems. These are problems that we encountered and we will encounter. There's two types of bearing. I wanted to do them kind of just side by side to make sure that you're clear on the two different ones. Typically, boat navigation uses this type, and typically aerial navigation uses the other. So let's just take a look at the first one here. So we've got somebody that's fishing 50 feet out from a tree and wants to position the line in the bait approximately north 35 degrees west of the boat and directly west of the stump. So the direction then from the boat, we want to go north and then 35 degrees to the west of that. That's where we want to position the bait, directly west of the stump. So the math in this one's not so hard. We just want to make sure that we're understanding how to use that type of navigation. All right, using a right triangle shown in the drawing, determine the reel's line counter setting to the nearest foot to position the line directly west of the stump. So we want to figure out what D is with that triangle. So does anyone have a question on how we identify where point B is, where we're trying to put the bait? So directly west of that tree stump and north 35 degrees to the west. All right, so we just have to find D in this case. And what trig function will be the trig function that connects that, and that? Cosine. So we'll do cosine of the angle, 35 degrees, and that's going to be adjacent over hypotenuse, so that's going to be 50 divided by D. So that'll be the equation we want to solve. This might be down here. Let's stretch that out a little. All right, so simple enough. We just did a bunch of these, so we'll multiply, divide, and then somebody type that into your calculator and get an approximation. And because this was rounded to the nearest foot, let's round D to the nearest foot. And what do we get? 60 what?
61.
61 feet. Thank you. All right, so that's that type of navigation. You go north or south, and then from that north or south position, you go east or west. Aerial navigation. Airplane travels at 120 kilometers per hour for 2 hours in a direction of 319 from Chicago. At the end of this flight, how far north of Chicago is the plane? We'll figure out both directions from the airport, but we'll at least answer that question. All right. So it travels in a direction of 319. This type of bearing for aerial navigation, we come off the North Pole and we rotate clockwise. Instead of off the x-axis counterclockwise, off the North Pole clockwise. So 319, we're going to rotate around, back up into quadrant 2. So 319, we have to just sort of keep in mind that each quadrant is 90 degrees. So there's 90, there's 90, there's 90. So 390s is 270. And then that leaves us with a reference angle here of 49 degrees. Are you okay with that? All right, so that. And now if we're going along this terminal ray, let's pick a point on the terminal ray. They say we're going to fly 120 an hour for 2 hours. So let's consider the moment that we've been flying for 2 hours will be 240 kilometers from the airport. And the question says, how far north of Chicago is the plane? The plane is also west of Chicago, so let's answer both. Let's use a triangle. So we'll pull out this triangle. And the reference angle that we're using is 49 degrees. And then let's just call these sides W and N for west and north. And then it's simple trig from there. So the hypotenuse is given to be 240. And if the question they asked was about north, so let's do north first. If we find the sine function of 49, that will be equal to opposite over hypotenuse, so that's n divided by 240. So n will be 240 multiplied by sine of 49. Somebody type that in, and let's approximate that to the nearest kilometer. Somebody get it? 181. Thank you. Okay, so that's the nearest kilometer. And because we used the letter N, we know that that's north of the airport in Chicago. And then to figure out west, we would use different trig function. We'll use cosine. Cosine 49 is west over 240. So west is the hypotenuse times cosine 49. And if we type that into our calculator and round to the nearest kilometer, how many do we get? 157. Thank you. So 157 kilometers. And that's to the west. All right, so on the test, just make sure that you're using the right bearing. If it's aerial, it's always going to be off the North Pole. And that's important because if you're flying at 319 degrees and you draw that in the wrong way, if you draw that like this, you're going to be south and east of the airport. So make sure for aerial navigation, clockwise from the north. Terminal ray approach to finding trig function values. You guys go ahead and try to figure out the 6 trig function values for that. And I'll get it set up here. First step in your process should be to find R. If you're feeling like you needed a clue. If not, you probably already found R. Points of caution, remember that when you're squaring a negative, make sure you wrap it up. If you want that -5 to square, you have to put the -5 in parentheses. If you don't put parentheses, the power of 2 does not touch that minus sign. Another quick comment, make sure that when you're writing down your trigonometric functions that you put an angle in there. Don't just write tangent equals tangent of theta equals. So you have to have an angle. A trig function has to be of an angle. Tangent equals doesn't make any sense. It's got to be tangent of something. Tangent of theta. All right, how about for sine? What'd you get? -5 over the square root of 29. So I didn't finish off my r here. R squared is 29, so r is root 29. We don't need a minus because r is distance. On the test, I don't care if you rationalize the denominator or not. If you want to, of course you can, but I'm not going to take off for that. How about cosine? 2 over root 29. And so just remember, the most common mistake here is for someone to say sine is -5 and cosine is 2. We know sine has to be between -1 and 1, and cosine has to be between -1 and 1. All right, so you've got to scale it by dividing by r. So don't forget the division by r. Tangent. Yeah. So we just do y over x. And now for these, we're just going to take the reciprocals. And that'll do it. Good. Now, let's just do a little extension here. The way I drew theta, I am saying, hey, let's use that theta. Let's use this partial rotation counterclockwise. So let's find theta. So to find theta, let's find theta, and I want you to focus on the reference angle here. So that reference angle is right down in there. And, what, is that the reference angle? No. Reference angle is right there. Sorry. So there's theta prime. Theta prime is always between the terminal ray and the x-axis. Terminal ray and the x-axis. And so to find the reference angle, let's do it two ways. You can use inverse sine. You could use inverse sine, inverse cosine, or inverse tangent. Let's just focus on sine and cosine. So inverse sine, and what should I put over here to get the reference angle? The reference angle is always a positive angle. It's always acute. So what should I put over here? If you look right there, and so should it be positive or negative or what? Positive. So to find a reference angle, we always do inverse sine of the positive. We take the absolute value. Or you could use cosine. And the cosine one's already positive, so it doesn't really matter. But if you do either of those, you'll get the same angle. If you left the minus sign in there, you would not get the same angle. So to get a reference angle, we take the inverse trig function of the absolute value of the other side. And let's just round this to the nearest degree. So make sure you're in degree mode. Inverse sine, 5 divided by square root 29, wrap. Make sure it's all cleaned up. And you should get about 68 degrees. And if you did inverse cosine, just double check. 2 divided by square root of 29, wrap. And you get the same thing as we would expect. Okay, so that's the reference angle. So what is that theta then that I've selected right there? So this implies that theta is equal to, how do we apply that reference angle to get that theta in quadrant 4? So we have an angle in quadrant 4, and we have to do something different for each of the 4 quadrants. So how are we going to get theta from that theta prime? Subtract it from 360, right? 360 would wrap us all the way around, and then we have to back off the theta prime. So if we do 360 minus 68, that will give it to us. That is how we would find theta using a reference angle there. All right, good. Any questions on that reference angle stuff? All right, let's go to this. All right, angular and linear speed. I'm going to ask you a couple more reference angle questions if we have time at the end. All right. In a circle with a 5-meter radius, how long is an arc associated with an angle of 2.1 radians? So this is getting at a really important formula that we had that connected a central angle, which just means an angle in a circle, coming from the center of the circle. So a central angle, the radius, and the arc. And that really important formula that we have gives us theta in radians. So we have to do the arc divided by the radius, and that will give us theta in radians. That formula is only true if theta is in radians. So it has to be in radians for that to work. Theta is in radians. So draw a picture. It's always, with trig, having a picture is really, really helpful. So we've got 5-meter radius, and we have 2.1 radians. So let's just draw something like that. Do you remember what 1 radian was equal to in terms of degrees? 57. Yeah, something like that. I would never remember that one for some reason. I can remember digits of pi, but not that one. It's like 54.7 or 56.7 or 57. Well, somewhere in the 50s, right? So something like that's about 2 radians. So let's figure out the arc. So if we look at that circle there, or excuse me, that equation, and I solve for s, s is going to be theta times r. Theta is 2.1 radians. That's good. If it was a degree angle, we'd have to do something different. We'd have to convert it. And then the radius, we're told, is 5. So this is going to be simply 105 meters. That will be the arc right along there. Yeah. 57.3 degrees in 1 radian. Never remember that. 57.3 degrees is 1 radian. So if you're just trying to draw your picture so it's relatively accurate.
Isn't that 10.5? Yeah.
Oh, decimal point. Thank you. Yes, thank you. Yes, 10.5. Good. So anything that relates these three, it's not hard questions. You just have to remember that's the formula that connects the angle with the arc and the radius. Not too difficult, but worth doing at least one. Okay, angle of revolution. Through how many radians does the minute hand of a wristwatch rotate from 1240 to 130? Through how many radians? So the minute hand has gone from there all the way down to there. We want to know how many radians. So think for a minute. You could try to use that formula that I just had up there, but there's actually a really simple way to do this. How many radians would a full revolution be? 2 pi radians for a full revolution. And we're rotating a fraction of a full revolution.
11 pi over 6.
So we could use a ratio. What did you say about pi over 6?
Is it 11 pi?
11 pi over 6. That's definitely a reasonable guess. So let's think about the proportion of a full revolution that we're rotating here. So if we count, there's 12 sectors all the way around. It's a 12-sector circle, a clock. And we're going to use all of them but 2. Everybody agree? So our rotation is through 10 of the 12 sectors. So our rotation is 5 over 6 of a full revolution. So if we take 5 over 6, that's our proportion of 2 pi that we want. So we end up with 5 pi over 3. That would be our angle in radians. So let's count if we want. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sectors. And we have 2 left over, so we use 10 of 12. So 5 out of 6. That's our proportion. We want to take 5 out of 6 of a full revolution. A full revolution is 2 pi, and we want 5 over 6 of that. We multiply 2 pi by 5 over 6. And that will give us the radian angle for that rotation. So we're figuring out a ratio of a complete revolution and then multiplying it by 2 pi. If we wanted it in degrees, if we wanted to figure out what that rotation was in degrees, we do 5 over 6 times 360, because 360 degrees is all the way around, and if we're going to go 5 out of 6 of the way around, we're going to multiply 360 by 5 over 6. All right, so that one's more of a head thinker than a real formula cruncher. All right, let's get to the formula crunchers. All right. So we had 2 types of examples that we focused on for these linear and angular speeds. We looked at the scenario with the gears, where there's a constant linear speed and varying angular speeds. So if there's going to be a constant linear speed here, so this is like the bike problem, pedaling the bike, a point on the chain or a point on one of the gears is moving at the same linear speed if you're pedaling along at a constant velocity. If you're pedaling at a constant velocity, a point moving on the chain has got constant linear speed. Okay. And then the other one we looked at, well, let me say one last thing. So constant linear speed, but the little gear has to spin faster than the big gear to keep up. If the big gear is twice as big, it's going to spin half the rotations that the little one's going to. The little one's going to spin twice as fast to keep up. All right. The other example we had was the merry-go problem, where you were at different distances from the axis of rotation. There we had constant angular speed, but we calculated that the further you were from the axis of rotation, the faster your linear speed was. So those are our two hallmark examples for linear and angular speed. This one, constant linear, but varying angular. The merry-go-round, constant angular, but varying linear. All right, so let's go for this one. So the little pulley has a radius of 7, big one radius of 10, and we're supposing that the little gear spins at 20 revolutions per minute. So let's go with the little gear. What is the angular speed of the little gear? So the little gear will be, let's call it, do an omega sub L for little. So 20 revolutions per minute. That's an indirect measure of the angular speed. We know that there are 2 pi radians per revolution. So the conversion to angular speed is pretty easy. You just have to remember that one conversion. And we'll just leave it in exact form. So in exact form, we'll leave the pi in there instead of moving the pi around. So let's just leave it in exact form, giving 40 pi. And then the revs cancel, so we're left with radians per minute. Radians per minute. All right, so that's part A. 40 pi radians per minute. Part B says, what's the linear speed? So we're imagining the edge of the gear. What's the linear speed if you're on the edge of the gear? Right, so for part B, we have to convert angular to linear. And the formula that we use is V equals omega R. So for us, that's our omega. So if we want V, and V is constant no matter where you are, so we don't have to put a subscript on the V. So we're going to take omega little and multiply it by the little radius. So omega little, 40 pi radians per minute. Multiply it by the little r, which we said I think was 7 centimeters. 7 centimeters. So that gives 7 times 4 is 28, so we get 280 pi. And our units would be centimeters per minute. And those are units of linear speed. So this was an example where we just erased the RAD. You know, we concluded that radians are really an indicator that you're not measuring your angle in degrees, and radians are really just a unitless number, which we got from that formula just a minute ago, right there. S is units of length, R units of length, so the units of length cancel, and theta in radians really is just an angle. It has no units. It's a unitless number. So that means you can put the RAD in there if you want, take it out if you don't want it. Linear speed, those are the correct units for linear speed, so in this case we take it out. All right, so that's the linear speed no matter where we are in the system. And then we've got to go back to the big gear and get the angular speed of the big gear. Well, we use the same formula that we just used. V equals omega r. V equals omega r, but we want to solve for omega, so we have to take v and divide it by r. So for us, we've got omega for the big gear is going to be the linear speed of the big gear divided by the radius of the big gear, and the radius was 10 centimeters. So we divide and we get 28 pi. Here the units of cms are going to cancel. And so we would have 28 pi blank per minute. So here we put back in the unit of radians because it makes sense. Angular speed should be angle per unit of time. So there is our angular speed for the big gear. How many revolutions per minute does the big gear complete?
14.
So 14, I hear. So there's a couple of ways we can get at that. And the mathematical way will be to convert that. So we have 28 pi radians per minute. And we know that one revolution, we're trying to get to revolutions, has 2 pi radians in it. And so that will give us 2 pi into 28 pi gives us 14. And our units are revolutions per minute. So that is our last one. And then the check on this, I'll ask you for each of those 4 along the way on the problem. And then our check is this. So this is 7, this is 10. So we can form a ratio of 7/10 or 10/7, it doesn't matter. Let's just form that for a minute. And we're told that the little one is spinning at 20 revolutions per minute. The big one is spinning slower, right? Big one has to be spinning slower. 7/10 is less than 1. So if we take 7/10 and multiply it by 20, that will shrink the 20 down a little bit. And 7/10 times 20 is 14, which is what we got as our final revolutions per minute. So that's a check that the ratio approach gives us a way to check our final answer there. We got the right answer. All right. So let's go through some of these guys. So really important that you've got your 2-unit circles down pat by now, and that you can pull off the coordinates on the unit circle really easily. All right, so let's start with 11 pi over 6. So write down the 6 trigonometric function values for 11 pi over 6. I think it's really, really helpful to draw a unit circle every single time you're trying to evaluate or find the 6 trigonometric function values. I think it's really helpful to draw a circle. You don't have to draw all the nodes on it, but just draw where you are. It at least helps you get the pluses and minuses correct. And it also helps you to get the 1/2 and the square root of 3 over 2, or whatever the coordinates are. It helps you put those in the right place. In order for us to proceed, we need to know the coordinates of that terminal point. We definitely need to be able to identify the coordinates of the terminal point. So any question on the coordinates of the terminal point? The 12-sector circle, we've got the 8 intermediate points, 8 intermediate terminal points. All of them, root 3 over 2 or 1/2. Root 3 over 2 is bigger than 1/2, so the longest leg is always going to be the root 3 over 2. 1/2 is always the shorter one. So when we're in quadrant 4 over here, the x is longer than the y. So the root 3 over 2 goes with the x and the 1/2 goes with the y. And then we're in quadrant 4, so y is negative. So what is sine of 11 pi over 6 then? Negative 1/2. So it doesn't matter how we got to that terminal point. Doesn't matter. But if that's our terminal point right there, that's sine no matter what. Whether we rotated this way, rotated that way, did multiple revolutions, doesn't matter. And cosine is root 3 over 2. How about tangent? Negative 1 over root 3, and I'm going to rationalize that to negative root 3 over 3. So one thing I pointed out was that the slope of this is minus root 3, and the slope of this terminal ray is minus root 3 over 3. So what I think about is the fact that this terminal ray, I think of that as being steep, and the steep one is going to have a slope of either positive root 3 or negative root 3, depending on which one you're on. And the less steep one is going to have a slope that's 1/3 as steep. It's root 3 divided by 3 and then plus or minus. Okay? So negative root 3 over 3, the less steep terminal ray. And then we do our reciprocating. And our reciprocating is pretty straightforward. And again, on the test, I won't mind if you don't rationalize the denominators here. If you want to, of course you can. And then this will be minus root 3. All right, let's do an 8-sector one. So let's imagine negative 5 pi over 4. So go ahead and do that one. Step 1, point on terminal ray coordinates. Any question about how we would get those coordinates? The 8-sector circle, all 4 of those intermediate points, they just use one number. Root 2 over 2. So here are these 4 intermediate points, all root 2 over 2. All right, so what is sine? Root 2 over 2. So once again, alphabetical order, cosine, comma, sine. We're on a unit circle. Cosine is negative root 2 over 2. How about tangent? Negative 1, it's the slope of the terminal ray. Negative 1. And then we'll reciprocate these guys. We get that. Give you one more to do. Let's see. I want you to do let's do one more of these. Let's do one with a whole huge angle. So find the 6 trigonometric function values for that angle. And to do that, you need to subtract off. So I want to make sure that you know how to subtract down to a standard angle, which is between 0 and 360. So figure out what the standard angle would be. So the coterminal angle, terminal rays are the same for coterminal angles, so subtract off your 360s to get down. Figure out what your standard coterminal angle would be. I'll just call it theta naught. Theta sub 0 equals what? So here are 180. So the way that I think is the easiest way to do this, if you take your big crazy angle and you divide it by 360, we get, what did I get? Did I get 31.5? Okay. Okay, 31.5. So what that means is it's 31.5 revolutions. So what I would do is that and then I would go back and say, okay, now let's take 11,340 minus 31 full revolutions times 360. And so that is going to leave us with 180. So that will be the standard angle that's coterminal. So what are the 6 trigonometric function values for that angle? Draw a picture if you have to. Always, if it's not coming right out to you, draw a picture. If you can't see it instantly, draw a picture and calculate it carefully. So we're going to look at our just a 4-sector terminal, 4-sector circle. 180 degrees just brings us over to a terminal point of -1, 0. All the rules still apply. That's still cosine, comma, sine. Has not changed. So what's sine? 0. And what's cosine? -1. And what's tangent? 0. Good. Cosecant? Undefined. Secant? -1. Undefined. All right, let's do one where we have some crazy multiples of pi. Let's make sure we can subtract off 2 pi's properly. All right, so let me do a 2 pi one. Let's see. let's do that one first. Let's do 27 pi. All right, so figure out first the theta naught, which just means a coterminal theta that has the same exact terminal ray. And what do we end up with that for that? What would be our theta naught if we want to rotate backwards 2 pi, 2 pi, 2 pi, 2 pi, 2 pi, 2 pi? Just pi again. So that's not so interesting. Let's change it a little. Let's put an over 2 here. Let's do that. Let's make it a little more interesting. Let's do that. That'll be more interesting. Because we just did a pi. Okay, so 27 pi over 2. How many full revolutions are we good to do? If you want, you can think of this as 13.5 pi if you want. I'm not sure if that helps or not, but it might. So we have to subtract off 2 pi's to be getting coterminal angles. So the first coterminal angle down would be 11.5 pi, 11.5 pi. And then 9.5 pi, 7.5 pi, 5.5 pi, 3.5 pi, 1.5 pi. So 1.5 pi is 3 pi over 2. Do you agree with that? So we have to, if I divide the 2 into there, we can think of this as 13.5 pi. And then we want to subtract off 2 pi until we get to an angle that's between 0 and 2 pi. So if we have 13.5 pi, the next angle smaller that will be coterminal will be 13.5 pi minus 2 pi, which is 11.5 pi. And again, brings us to 9.5, 7.5, 5.5, 3.5, 1.5. So 1.5 pi, 3 pi over 2. And that puts us on the low side. 3 pi over 2 is down below. That point is 0, negative 1. There's our theta naught. Co-terminal angle to theta. So what is sine in this case? Negative 1, 0, and how about tangent? Undefined. And then reciprocal, reciprocal. And how about cotangent? 0. So that one you've got to be a little careful of. You might say, oh, undefined divided by undefined. Or if you take the reciprocal of undefined, it should be undefined. Be careful there, because by definition, cotangent is the x value divided by the y value on the unit circle. So if we come over here, x divided by y is 0 over negative 1, and that's 0. Good? All right. So next, a couple of questions. So find theta prime if theta equals 200 degrees. Find theta prime if theta equals negative 5 pi over 4. Let's do those two reference angle ones. depend on the quadrant that you're in. So if you haven't drawn a picture, you might want to draw a picture because the reference angle is always between the terminal ray and the x-axis. So if you don't know what quadrant you're in, you're not going to be clear on what you should be subtracting or adding to what. So I would definitely recommend drawing a picture. And 200 degrees is going to be somewhere over here in quadrant 3. So that's going to be your 200 degrees. So then what's the reference angle? 20 degrees. So theta prime is 20 degrees here. So the reference angle is always the angle between the terminal ray and the x-axis. All right. Now, how about that one? Negative 5 pi over 4. That one's going to take us into a different quadrant, so we're going to have to do something slightly different. That is a multiple of pi over 4, so I'm going to actually grab an 8-sector circle, since I know we're dealing with a multiple of pi over 4. So, negative 5 pi over 4, there's 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. Takes us to right there, that terminal point. And what is the reference angle then? Pi over 4. So it's always the angle between the terminal ray and the x-axis. So theta prime there is going to be pi over 4. All right, so let's use a reference angle approach to solve the following question, following problem. Suppose we have tangent of theta is equal to 10. Find theta in quadrant 3. Theta is in quadrant 3. Figure out what theta has to be. And just round to the nearest degree. First step is to find the reference angle. The second step is to use the reference angle in the quadrant that you're in to come up with theta. So find your reference angle to the nearest degree. It'd be really simple if theta was just inverse tangent of 10, but that's not the case. So if let's go down. So if we're in quadrant 3, so let's get a little bigger than that. Quadrant 3. So the tangent of theta is 10. So that means that the slope of the terminal ray is pretty steep. Right? It's because the slope is 10, so I'm going to draw it pretty darn steep. Draw it like that. Quadrant 3. We know that in quadrant 3, the reference angle is right there. That's theta prime. So we want to use that theta prime to calculate. Let's use a different color for theta. So there is theta. So we want to use the reference angle to calculate theta. And the way we find a reference angle is to take the inverse trig function of the absolute value of the other side. In this case, absolute value 10 is 10, so it doesn't really matter. But that's a good habit to get into. So when you do inverse tangent of 10, you get 84 degrees. 84 degrees. So what is theta then? So it's going to be 180 plus 84. So everybody see that in quadrant 3, you add the reference angle to 180. So that'll be 264. So if you look at the picture, that's why it's so important to draw the picture, because if you look at the picture, it should make it a little more obvious. If we are trying to find the measure of this blue angle all the way around there, that blue angle, we're going to go to 180, and then we have to add that red piece. The red piece is the part we found with our inverse trig function, so we're going to add 180 to the reference angle. That will give us our angle in quadrant 3. Okay. Let's try this one. Do another one of those. Let's suppose we have cosine of theta equals negative 1/3, and theta is in, let's go with quadrant 2. So find theta in quadrant 2 that has a cosine value of negative 1/3. Quadrant 2, cosine is negative 1/3. So if I'm going to draw a terminal ray here, that point, the x value of the terminal ray, or the x value of the terminal point, should be about 1/3 of the way across. So I'm going to draw it about like that. So there's our terminal point. The angle we're looking for is right here. That's theta. We have this as our reference angle. And how do we, oops, that should have a prime on it. How do we find theta prime? Inverse cosine absolute value. We get that. Type it into your calculator, and what do you get? 71?
If you round up.
71 if you round to the nearest degree. So then theta is equal to, when we look at that picture, if you don't draw the picture, it's a little harder to sort of piece it all together. But when you look at that picture, what's theta have to be? 180 minus the reference angle. So we're going to do 180 minus the reference angle, and that's going to be whatever that is, 109? 109? That make sense? Let me think about another one that tends to be. Let me have you guys do one of these. We did one earlier today, but let's just do one more. So, because it's definitely a good test question and it's important to get down pat. So, find the trig values for theta if 6, negative 2 is on the terminal ray. Let's do that. sure you got that down. Should be pretty quick. All right, so step one, hopefully you're jumping right to it. 36 plus 4. You're finding the radial distance. And this has a perfect square embedded in it, so make sure that that's comfortable to you. You've got to reduce your perfect squares. So you should have 2 root 10. And then for sine, which coordinate, y or x? Y. Is anybody having any trouble with that now? Sine is y, cosine is x. Okay, so sine is going to be the y coordinate divided by the radius. And that's going to be, the 2's are going to cancel, so we get negative 1 over root 10. You can rationalize it if you want. Cosine is positive 6 over that, so you're going to get 3 over root 10. Tangent, y over x, so negative 1/3. And then flip them all over. Get that. Any of those function values cause you grief? All right. Steady weekend. Steady weekend. Study hard. And I'll see y'all on Tuesday. In the website, there's also I have a study guide up there also that you can go through that has some highlights for Chapter 6 under content, under study guides. All right. Have a great weekend.